All right, so the first one's just the binomial coefficient, and I would do 8 factorial over 8 minus 3, which is 5 factorial times 3 factorial. Break down the 8 until it hits the 5. Again, I line up the 5s. You don't have to. You can put them anywhere you want, but I line them up just to remind me what to cross out. These are going to cancel. 2 goes into 6 3 times, and then the 3 cancels, and I just get 8 times 7, which is 56. Remember, those should always be whole numbers, so if you get something that's a fraction, something's wrong. All those binomial coefficients should be whole numbers. And like I said, you probably won't get a straight-up question that's just the binomial coefficient. It's going to be built into, like, find this specific term. And also, we're going to use those when we get to, which you'll see, when we get to 8, 6, when we start to talk about combinations. All right, number 2 says write the expansion of the expression. So I'm going to write it out, like, fully with the C's, just in case you do it that way, and then we'll talk about Pascal's triangle. So because the exponent is 3, my n is 3. How many terms should my answer be, though? 4, always one more. So the first part is going to be C3, 0. Then I'm going to get C3, 1, C3, 2, and C3, 4. No, sorry, 3, 3. Then the second part comes from this first term to the highest exponent decreasing. So it would be 2x to the third, 2x to the second, 2x to the first, and 2x to the 0. And then the third part comes from this second term, which has a negative, and that negative is important. I have to keep it with it. This one, we start at 0 and work our way up. So this would be negative 3 to the 0, negative 3 to the first, negative 3y to the second, and negative 3y to the third. And right now they're all sums, so it's all plus in between. But the negative on that 3 is going to change some of those. So now I'm actually going to skip to the next question and work out the Pascal's triangle just because we can grab one of the rows from there. And then I'll come back to this. So if I had done C30, C31, C32, and C33, we would have gotten this same pattern, but this is 1, 3, 3, 1. So that's the C part. So I get 1, and then 2x to the third is 8x to the third, and then negative 3y to the 0 is 1. So that first term is 8x to the third. Then I go to the second one, so I have 3 from the coefficient. 2x to the second would be 4x squared, and then negative 3y to the first is negative 3y. So this time it's negative because I only have one minus, so I get that negative. And then 3 times 4 is 12. 12 times 3 is 36, x squared y. Then I go to the next one. So the next one, I get the 3 from the coefficient. 2x to the first would stay as 2x. And then negative 3 squared is 9y squared. 3 times 2 is 6, times 9 is 54. So 54xy squared. And then the last one, C is 1, 2x to the 0 is 1, negative 3y to the third is negative 27y to the third. So minus 27y to the third. And that should be your expanded binomial. Questions on that one? So I haven't decided yet what calculator I'm going to let you use next week. Because to be honest, almost every scientific and all of the graphing calculators have a C button. So you literally just like type CNR, like you just type it in and it does it for you. And when we get to permutations, you'll have the same thing. I want to give that to you, but if I give that to you, I need to see all this work. So I'm going to be really picky about your work if I do let you use your graphing utility. I just want you to remember that. And I'm going to watch you like a freaking hawk, people from home. There will be no hands off screen. It's just not fair that people from home have that environment and people here do not. So I'd like to give everybody a level playing field. I don't want to slam you with a test that you can't finish because of timing. But I also want to test your brain and not your calculator. So I will let you know for sure 100%, but I'm leaning towards total use of your calculator, but then that means the questions will be tweaked a little bit. Yeah. No, you can use a triangle.
No, I know, but do you still want us to see the C's, like write it out?
You can, like, as long as you write out the next parts, I'm fine with you using the triangle for the C's. Yeah, that's fine.
So I could just write like 1, 3.
Yeah.
So So even if we have our calculator, we don't need to like do the C's with the two.
Correct. Right? Yeah, but like, which you won't get a question that's just like this, but your calculator will do that.
Okay.
So you don't have to do any work. And normally I would split up this test, but I don't want to wait. I have to give it Friday, and I don't want to wait till the following Wednesday. Just like a long time in between. So I'm toying with giving you everything on Friday and then letting you use the graphing utility. Yeah.
So we can do all the problems without a calculator if we wanted to.
Yeah, when we get to, you're going to see when we get into probability, the numbers are going to get higher. Those you're going to want the calculator for. And then there's some that you actually have to divide to get a decimal, turn into percent, that you need the calculator for. You could use a basic one for it, which that's kind of like where I'm on the fence. Like I could let you just use a for function. That's kind of what we've done in the past. But I can see what you guys are using, and it's not as fair at home. So.
Okay, so at least for the lessons that we've done so far, we don't need like a graphing calculator.
Correct. Yeah. So first 6 rows, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. So 1, 2, 3, 4, 5, 6 rows. Okay. And for that last question, because we raise it to the third power, we would want we raise it to the. All right, so we already did the Pascal's triangle, and now we're going to the sixth term of 3a plus b to the seventh. So if it's sixth term, what's my r? 5, good. What's my n if this is being raised to the seventh power? Seventh power.
Oh, sorry, I thought we were doing the other thing.
That's okay. It would be 7, right?
So R is minus the term, not the power.
Correct.
Oh, I see. Okay.
Because it would be, the r would be 0, then 1, then 2, then 3, then 4, then 5. And if you count that out, 1, 2, 3, 4, 5, 6, that would be the sixth term. So r is always 1 less than the name of the term, if you want to think about it that way.
So if it's the triangle, the 1 is 0. Like
The 1 is row 0, yeah.
So,
If you were to, because think about how you do your C's, right? You do C and 0 is the first one. That R is 0, the first one. Does that make sense? God bless you. That's why I think it's more confusing to use the Pascal's triangle to get, God bless you, an individual term. It's great for the full row because you can say, like, I need 7 terms and my N is this. That's easy. But to do something like this, it's easier to know how to do C and R. Okay, so then it's C and, speaking of, C and R. So C, 7, 5. First term, which is 3a to the n minus r, so 7 minus 5. Second term, which is positive b to the r, which is 5. So I can do 7, 2, 5, 7 times 6 times 5, over 2 times 1 times 5. These cancel. 2 goes into 6 3 times, so 21 is my C7, 5. And in a moment, I'll show you how to do that on the calculator. And then this would be 3a to the second. So 3 to the second would be 9. And then a squared, and then b to the fifth. And then 21 times 9 would be 189, a squared, b to the fifth.
Oh my god, I got it right.
Yeah.
for this one I used the triangle, but I did whatever row it was with 8 terms, and then I just counted.
That's fine.
Oh,
I just think it gets confusing. It doesn't mean you can't do it.
Oh.
Yeah, people just screw that up.
Okay.
Yeah, but if you're good, no, yeah, it doesn't matter how you do it. Remember I said I would probably write out my Pascal's triangle on my reference sheet. Like, it's going to be there, so you might as well use it. Okay, so, all right, so if you have the newer, which I think it's the 84, just the regular 84 and the 84 plus, if you go to, oh, this is funny, I don't remember where it is. It's under math, probability. So I went to the math menu, and then I went over to probability. And the third thing in the row there is your NCR. If I hit that button, it gives me the little subscripts, and all you have to do is type it in. So if I'm going to do 7, 5, let's say 7, 5, and then I hit enter, and there's my 21. Okay. Notice on that same menu, math, arrow over to probability. Number 4 is your factorial. Okay. Obviously, we're going to need that when we get into probability. So keep in mind those are both under that menu. On the older calculator, okay, when you go to that same menu, so if I hit math and I arrow over to probability and I go down to NCR, it doesn't give me the little subscript boxes. So when you're using this calculator, you first have to type in N, the one on the left, which is 7. Then I go math, I arrow over to probability, I go down to NCR, and then I hit R, which is 5, and then I hit enter, and it gives you the same answer. Most scientific calculators do something like that. So let me see if I have the other pink one, because a lot of you guys have this one. 800 calculators. This is how you know you're a nerd or a math teacher. Okay, on this calculator, there's a PRB button. If I hit it, there's my NCR second thing there, and it looks just like the brick one. So you have to do the order the same way. You're gonna do 7, PRB, go over to NCR, and then, what was it, 5? Yeah, 5, and hit enter, and there's my 21. So almost every calculator has it, obviously not the 4 function ones. So it's important to know, I would give yourself 2 options, a scientific and a graphing one, but most likely if I'm gonna give you scientific, I'm gonna give you graphing, because graphing is not what's the problem this time.
Miss Chris Wiley,
Yeah,
can you do it on the blue calculator one more time?
sure. All right, so this one, you don't have to type a number in first. You just go to math, you arrow over to probability, you go down to NCR, which is 3, and it gives you the little subscript boxes. So you just type it in, 7, 5, enter. Good on that one, Christina?
Yes,
Okay,
thank you.
you're welcome. All right, I'm gonna work through these homework questions. A lot of them are the expansion binomials, so I'm gonna try to do them a little bit fast so that you, excuse me, we can find your mistakes. And if I can like figure out which exact one it is, I'll do that. Like, cause this term, who was this? This was, yeah, no, this was this was Emily, right? This is 4. You had 6, right?
Oh, I didn't have anything in front of that. Oh, wait, yeah, I had.
Yeah, you had 6. Okay, this was Emily's. So Emily, you got the first, the second, the third term is where? And then I think, oh, the third down. Okay, so this would have been C, the exponent's 4, so that'd be 4, 0, 4, 1. So we're looking at C, 4, 2, C, 4, 3, and C, 4, 4. And then we start off with, this would be 4 to the third, so this would be 4x to the second, 4x to the first, 4x to the 0. And then the other way for the 7y, so this would be 7y to the 4, 7y to the 3, 7y to the 2. So C4, 2, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This would have been 1, this would have been 4, this would be 6. 16x squared, ooh, 49, holy moly, y squared, plus C4, 3, this would be my 4, so 4, 4x to the first, 7 to the third, that's 289, right? Nope, 343. Y to the third. And then C4, 4 is 1. 4x to the 0 is 1. 7 to the fourth is 1372. Y to the fourth. So then I'd get, wait, did I do something wrong? Why does that last one 2? Did I cut that off maybe? No. Oh, I wrote times 4. 7 to the fourth is 2401. All right, so the first one is 6 times 16 times 49, 4,704. x squared, y squared. So that's really the third term, which is the first one you got wrong. Then 4 times 4 times 343. 5, 4, 8, 8. X to the first, y to the third. And then 2, 4, 0, 1, y to the fourth.
Memorize that.
Okay, that's fine. So this would be 1, and then the first term x squared raised to the fourth, and then the second term y squared raised to the 0. And then 4, second term raised to the third. First term raised to the third, second term raised to the first. Then 6, first term raised to the second, second term raised to the second. Then 4, first term to the first, second term to the third. And then last one, first term to the 0, second term to the fourth. So I get x to the second raised, oh, did you add them?
Oh, yeah.
Yeah, you're raising a power to a power. So it's multiply. Easy fix.
So whenever you have,
So if I'm raising a power to a power, you multiply. If you're multiplying two, that's when you add them.
so like if I were to expand the y times y to the second times y to the second times y to the second, oh, that would.
Yeah, then you'd add them up.
Oh, okay.
Does that make sense?
Yeah.
Okay. Okay, this is, all right, then Christina, this is you. Okay, so the nth term, if n is 5, that's what it means, the fifth term. So remember, it's 1 less than its name, so r would be 4. Oh, you just forgot your a, Christina.
Yeah, I just noticed.
Okay, that's it. The rest is right. All right.
Where am I sick?
All right, so we're just going to get started on 8.5 today, which is called counting principles. This lays the foundation for probability. So 8.5 is called counting principles, and then 8.6 is really probability. So we're going to start to talk about the basics of it today. Right? The first is called just a simple counting problem. So if you're just straight up saying, what's the probability that I'm going to pick something out of something, the most basic form of probability, all you do is put the number of what you're looking for over the total number of items in the set. So if I have the colors of the rainbow and there's 7 of them and I'm saying what's the probability I'm going to pick red, there's only one red, I put 1 over the colors of the rainbow, which is 7. Okay, that's the most basic foundation of probability. So if the question was find the even numbers between 1 and 10, I would write out, if you need to, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And between number 10 would be 2, 4, 6, and 8. And between means don't include those. If it said inclusive, then I would include it. So there are 4 out of the numbers between 1 and 10, which is 1, 2, 3, 4, 5, 6, 7, 8. 4 out of 8 would always simplify to a half. So when you're writing your fractions, they will always be simplified. If it says something about rounding it or giving a percentage, then you would put it in that format. But normally we're going to leave our answers in these cases in fraction form. This would obviously be the same as 0.5 or 50% if it asks for it in terms of that. If it's, some of these questions might be multiple choice, so if it's multiple choice, it would be straightforward as to what format it's in. If it's standardized test, it's obviously going to be straightforward. If it's not, then I'll tell you to either round it or give it as a percent. If not, default is always the fraction. All right, then we need to know the difference between with replacement and without replacement. So when you replace something, what do? If I took a lollipop out of the box and then I replaced it, what did I do?
Just kept it.
You put it back. Yeah?
Oh.
So if I take something and then I replace it, means you put it back. So if you have a set and you use replacement, Jacob, wake up. It means you take it, but then you put it back, which means the next time you go to do something, that set is the same. It's unaffected. If you don't replace it, so something without replacement means you took it out and it's gone. So like you're doing with my candy, when you take it out, you eat it. Yes? So you don't put it back, thank God, because that would not be good, especially right now. Okay? You take it. Now, without replacement means that what's next for the next person to pick has been altered, right? So the set is now different than it was. If I was going back to like the colors of the rainbow example, if I take out a color and I don't put it back, the next person comes along, now there's only 6 colors to choose from because one's gone. Does that make sense? So that's the difference between replacement and without replacement. So this example says determine the number of ways in which a computer can randomly generate one or more such integers or pairs of integers from 1 through 15. So a lot of times when we're first getting started, we want to see the sample set. So you can feel free. Oh, I just skipped 7. That would be good. 7, 8, 9, 10, 11, 12, 13, 14, 15. So the first one says, determine the number of ways. So we're not looking at probability yet, just the number of the sample space. Determine the number of ways in which a computer can generate an odd integer. And it says from 1 through 15, so now we're including those numbers, okay? So how many odd integers are from 1 to 15? There would be 1, 3, 5, 7, 10, 9, 11, 13, and 15. How many are there? 8. Okay, there are 8 ways that a computer can randomly generate an odd integer. Jacob. B says an integer that's divisible by 4. So which of these integers are divisible by 4? 4, 8, 12. How many were there? 3. And it says integers, okay, because it doesn't want you to think about the decimals and the fractions in between these numbers, just these whole numbers. So a computer, you're always considering that it replaced that number. It's not gone. So a randomly generated number from a computer, you assume you start with the same full set every time. You start with the same 15 every time. This says 8 pieces of paper are numbered from 1 to 8. So again, I got a sample space of 1, 2, 3, 4, 5, 6, 7, 8, if you need to visualize it. 1 piece of paper is drawn from the box. Its number is written down, and the piece of paper is returned to the box. Then a second piece of paper is drawn from the box, and its number is written down. Finally, the 2 numbers are added together. How many different ways can the sum of 12 be obtained? So the long way around this is pick all the numbers, right? So if I pick a number, I put it back, and I pick again. That means the first time I pick, if I pick 1, the second time I can pick 1 with 1. I can pick 1 with 2. I can pick 1 with 3. I can pick 1 with 4. I can pick 1 with 5. I can pick 1 with 6. 1 with 7 and 1 with 8. So I could go all the way through that, right? Or you could set up a little, like, it's up to you how your brain works. But I could do this vertically. And then the second set vertically. The second full set because it's been replaced. And I could say, okay, 1 could go with 1. 1 could go with 2. 1 could go with 3. 1 could go with 4. 1 could go with 5. 1 could go with 6. 1 could go with 7. And 1 could go with 8. And you have to do that a long time. No, but that's your sample space. That's not how many can sum, right? So then the shorter way is to try to figure out what numbers I could add together to give me 12. So 1 plus any of those numbers, is that going to give me 12? No. What's the smallest one I can add to the biggest number to get 12? 4 and 8. So 4 and 8 is one combination. If I pick 4 the first time and then I pick 8 the second time. What else works? 5 and 7. Pick 5 the first, 7 the second. 6 and 6. 7, 5. 8, 4. How many are there? 5. Now, it already took care of those 5, and think about what happens if I worked backwards. What if I picked 8 the first time?
At this time, please send the
12th grade NHS members to the gym for their picture, 12th grade NHS members to the gym. And thank you again for your cooperation.
Isn't 4 and 8 and 8 and 4 the same thing?
Yes. So sometimes you have to work down and back up again, but this time we already have the backup. So I already have, if I picked 8 the first time and 4 the second time, I already have that. If I picked 7 the first time and 5 the second, I already have that. Okay? So sometimes you have to work both ways. I don't know if that makes sense. But this time it's taken care of. So there are 5 total ways to get the sum of 12 by pulling these pieces of paper out. Okay, example 3, almost example like the last one. It says 8 pieces of paper numbered 1 through 8 are drawn, placed in a box. 1 piece of paper is drawn from the box, the number's written down. The piece of paper is this time not returned to the box. So how does that change things? The second time there's less of a pile to choose from. So in the first one we had 4 and 8, 5 and 7, 6 and 6, 7 and 5, 8 and 4. Are all of these possible the second time? If I take out 4, 8's still there to grab, that works. If I take out 5 and don't replace it, 7's still there to grab, right? But what happens with the 6 and 6? If I take 6 out the first time, it's not there to grab the second time. Does that make sense? So this cannot happen this time. So now there's only 4 choices, or no, only 4 ways. Again, if you want to write them out twice, like if you need the visual, do it. If you wanted to write the numbers 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8, with replacement, those full sets stay both times. But this one without replacement, if I pull the 4, that 4 is gone from my second set. So I can't pull 4 twice, right? I can still pull 4 with 8 though. If I pull 5, I can still pull 7 because it's there. The 5 is what's gone. If I pull 6, I cannot pull the 6 because it's gone. Does that make sense?
So you just can't pull the same number?
You can't pull the same number twice. Correct.
So the only ones that wouldn't work would be the ones that have the same number both times.
Right, for now. Eventually we're going to start talking about like what's the probability of each of those happening. And then you have to remember that the beginning, it's 1 out of 8 because your sample space is 8. But the second time, it's 1 out of 7 because one number's already gone. Does that make sense?
Yeah.
Okay. All right, the fundamental counting principle, and I think we'll stop after this, says let E1 and E2 be 2 events. So 2 things that are happening, whether they be rolling the dice twice, pulling a card twice, pulling a piece of paper out of a hat twice, okay? Each of those is a separate event. The first, and that should be event, one of these years I'll correct it. The first event can happen M1 different ways. And then after E1 has occurred, E2 can occur M2 different ways. The number of ways that 2 events can occur is M1 times M2. So the number of ways that they both occur. So this is an and, because eventually we're going to get an and or. So if I roll a die, how many different options are there the first time I roll that die? 6, right? 6 sides on a die. So if I roll the dice twice, there are 6 options the first time, and how many the second time? 6. So the number of ways, the different combinations I can get from that is 36. So when we're figuring out the number of ways these events can occur, it's each individual event times each other. So this is how many different pairs of letters from the English alphabet are possible. 26 times 26. So there's 26. We're not saying anything about replacement or non-replacement, which means it's the full set each time. So 26 times 26 is 676. A combination lock will open when the right choice of 3 numbers from 1 to 30 inclusive, which means include 1 and 30, is selected. How many different lock combinations are possible? So 3 numbers. The first number has how many choices? 30. The second number has how many choices? 30. The third number?
30.
Good. So my answer, how many different ways?
30 times 30 times
Good.
A big number.
No, that's not 9. Just kidding. 27.
227 something.
27,000 ways. Okay. If it had said something about like the numbers not repeating, that's when it gets to be a little bit different. That we'll pick up with tomorrow. All right, folks, we will finish the notes for this section tomorrow. If you want to get a head start on the homework, you can. I'll write on there like where we left off, what number you can get to. If not, you're leaving it all for tomorrow, and it will feel like a lot.